So. Dann legen wir langsam mal los. And we switch to English. So this is Kai, I'm Matthias, and today we want to show you some insights into machine learning without the data. So how to do machine learning while keeping privacy-preserving data. And to start, at first, we will look into the privacy transparency dilemma. So on the one hand, you have privacy and it's important. On the other hand, you have transparency, so using the data, and it's important as well. So there is kind of a dilemma and trade-off, and we will talk about this. And then we will have a look into solution technologies. So what are technologies out there that are tackling this dilemma? So we can have both privacy and transparency. And last but not least, we will look into code and we will program a fully working federated learning example using the framework called Flower and do some live coding. So let's start.
Yeah, so first we're going to talk about the privacy transparency dilemma. First of all, we're going to go into privacy and into transparency and then into privacy. So the idea here is that we can have transparency and make good products and good machine learning models. And on the other hand, transparency tries to preserve our privacy and not leak any private data to the outside. So transparency. I brought you an example of genome data. So for example, if I wanted to find out information about my own genome data, I would probably need to upload it somewhere and give someone else my data, hence making it transparent to someone to gain insights, because I don't have the tools at home to do that. With that, I can gain interesting information about myself, like maybe what's the best diet for me or what diseases I'm prone to. So that's about transparency. I can build good products with it. And next one is privacy. So let's have an example with cancer detection, where we want to build the traditional machine learning model, and we have data in 4 hospitals. So to train a traditional machine learning model, we would want as much data as we can get to get the best model that we can get. And for that, we would centralize this data. So we would take the data from our 4 hospitals and put it on one single server and use that for cancer prediction. But that's not so easy, because you can't just move patient data from a hospital. So let's talk about centrally storing private data. So for example, in Germany, it is forbidden to just move patient data without their consent away from the hospital. But we want to train a good model, so we cannot do that. So why is it forbidden? Let's say you have a bank account and it gets hacked and someone steals 100 euros from you. Then the bank could just go ahead and give you back your money. So that's not a problem. But if a medical report of you gets leaked, that maybe you're HIV positive or something like that, and that becomes public knowledge, you can't just compensate that with money or anything else. That is public knowledge and it will stay public knowledge. So it's really important to be very careful here. On the other hand, for other kinds of data that is not so sensible, it might be allowed but unaccepted by people or society. So for example, the Corona Warn app was initially planned to be implemented in a centralized way to centrally store movement and contact data of their users. But because people spoke up about it and were unhappy about it and probably not use it in the end, it was no way to go, and they implemented in a decentralized way, leading to way more users than it would be without, I guess. So we saw that we can make good products with transparency, but we should be careful about violating our users' privacy. And let's look if we can have some solution technologies that make it possible to maybe have both transparency and privacy at the same time. First one is homomorphic encryption. Homomorphic encryption allows us to compute on data that we cannot see. So, for example, encrypted data. So I brought you another example where we have an encrypted data set. So let's go with the genome data again and say we have a data set with different DNA data along with my own. And I want to make computations on it and find similarities or something like that. And the only way I have is to give it to an untrusted cloud to do these computations, because again, I can't do that at home. So with homomorphic encryption, I can encrypt my data set, pass it to an untrusted cloud, and get encrypted results back. So here the data stays encrypted at all time, and the untrusted cloud gains no knowledge of my data. This sounds pretty nice because it fully preserves privacy and offers transparency at the same time. But it's not really feasible at the moment. Homomorphic encryption at the current state is not really feasible to implement in practice because it's very limited in what it can do. And you can do certain stuff, but it's very, very inefficient and not practical to use. So let's look at a different technology that we can maybe use, or that we can use to make privacy-preserving machine learning. So here we have an image of me and a dog opposing to traditional machine learning. We don't go with cats here, we go with dogs. So I have this image and I want to train a dog classifier on this image. But the problem is that there's my face in it. And that is private data that I don't want to put on some cloud where I train my model. So that would compromise my privacy, and that's not good. So what can we do about it? We can, for example, add noise to the data so that my face is not really recognizable anymore, but I can still have enough transparency so that I can train a dog classifier on this. And this concept is called differential privacy. We again see the trade-off between transparency and privacy here. So if we have a few noise, we can get better results, but we have less privacy. And on the other hand, if we have very high noise, the results get a bit worse, but still preserve privacy. So in the end, it depends on the sensibility of the data that we have. If it's more sensible, we might have more noise. And if it's not so sensible, we don't need that much noise. But of course, we always need to preserve the privacy, so enough noise so the privacy is preserved. And this is just an example for image data. This can also be done for other kinds of data. So that's really cool.
So let's come to the third technology we want to introduce to you, and this is federated learning. And for federated learning, the main idea is that we have a server where we have our centralized model. So it's pretty similar than a centralized setup for machine learning training. And we have the data on some clients or edges, like smartphones or industrial machines or some other hospitals. And the data should stay there because it's private, it's sensible, and it shouldn't leave the edge. So what we are doing now, in the first step, the server is distributing the model to the edges, just sending it out. Then the model is trained, so the quality is increased locally on the edges. So the edge trains on local data, and then is sending back the model update to the server, and the server just aggregates all the models he received from the clients to another main model. And this new main model could then be sent out again to the clients or used there or just be trained for another round. So this is the main concept of model-centric machine learning, federated learning. And we want to dig deeper into this. So I brought you an example about Pneumonia, so Lungenentzündung in German. And we will now write a fully federated learning setup using the Flower framework. And we chose federated learning because it's one of the technologies that is pretty good developed right now. So it's usable in production environments and it's pretty easy to use. For our example, we chose the hospital example we were talking about. So we have a hospital, and the hospital is interested in training a model to help doctors identify pneumonia in X-ray chest images. So in the hospital doesn't have too much images of chests with pneumonia and without pneumonia. So it's very hard to train a model, and there weren't good results. So it's a problem because these data cannot be shared with other hospitals or outside world because you don't have the consent of the patients. And so it's legally restricted. But what we can now do if we have 4 hospitals and they work together and they are not allowed to share the data, but we can now train decentrally on the hospital side and aggregate the models afterwards. We can have a central model in the end that is good in identifying pneumonia in chest X-rays. So what we have here is a binary classification. So we will classify these images in normal and has pneumonia. And what we want to implement now is, on the one hand, the server side, so server implementation. And the server is responsible for selecting the clients for training and evaluation, so the hospitals in our case. He managed the whole training, like sending out the models, collecting the models back, and in the end, aggregating the model in a way. And we will implement the clients that are responsible for defining the model architecture, like what kind of model we want to use for training, that just loads the private local hospital data and then does the training and the evaluation. And for our example use case, I used the pneumonia MNIST, which is the data set of around 6,000 chest X-rays that are labeled with a pneumonia or not. So let's dig deeper into code. So is it readable? Yeah, quite big. So let's go with this. So we will start with the server. So for the server implementation, I load the Flower framework, and then I need to define a strategy. A strategy is like the main part of the server defining how to act, like how many clients do I need for training? How many do I need for evaluation, or in general, how should I aggregate the models afterwards? So there are different algorithms for aggregation, like we will use here federated averaging, what is doing a weighted average of all the models. So we need to start here with our strategy. So let's define it. And Flower just brings a lot of strategy classes prepared, so we don't have to do too much here. So we choose the federated averaging, and the most important parameter for us here is the minimum available clients, because we want to wait till all 4 hospitals are connected before we start our training round. And then we need to start the server, of course. And for our server, of course, we need to hand in our strategy. And we need some server address. So let's start it on localhost port 8080. And that's it already. So this is the, I would say, most minimal part of a server you can write with Flower. So just like wait for 4 clients, start it, send out your current model, collect the models, do federated averaging, and do it again if I need more rounds, but this is just for 1 round right now. So let's come to the client. I prepared some code here, like some imports, basic imports. I need Flower again, of course. And then I'm importing some Keras classes, so I will use Keras for my model. I just go quickly over it because it's not in the focus here. So my model, it's a pretty straightforward CNN. So it's a model architecture that is good for classifying images. I use Adam for optimizing. It's a binary classification. I use binary cross entropy here for loss, and I'm interested in the accuracy. As I said, if you're not too aware of all these, it doesn't really matter. So you define your model somehow. And I need the local data. So here I have a partition parameter, and I have 4 worker files that I can load with the 4 hospital data. So this function is just loading the data regarding the partition. So I will start clients for the partitions 1, 2, 3, and 4. And to look in the main code, here I read just the partition parameter. I'm creating my model. I'm loading data. And then I start my Flower client. Here I will use the Flower NumPy client. It just has a lot of stuff prepared behind the scenes. And I choose the server address localhost 8080 and use my model I will implement right now. So let's come to coding. I have my constructor just setting model training data that is handed in. And then I have 3 functions I need to implement when I want to use Flower. So at first I have get parameters. This is a function returning the current local model, so the server can request the current state. Then I have my fit function that is receiving the current model from the server, does some training, and then sending back the information the server needs. And I have the evaluate function, so pretty similar, but instead of training, I'm doing evaluation because on the server, I don't have the data, so I cannot do the evaluation. So let's code this. I have my local model, and just to return my model, I'm just returning the weights from my local model. That's it already. For fitting, I receive the parameters from the server model. So the first thing I need to do is setting my weights from my local model to the parameters I received. And then just start the local training. So I'm doing a fit on my model, using my local train data. So with this, I'm really only training locally, so the data is not sent to the server. Let's set some more training parameters. So let's train for 50 epochs and use a batch size of 128. And then we return the response to the server. We need to return, on the one hand, the new model we just trained. So here again, getting our weights. Then we will return the number of training samples we used. This is important because, as I've shown you, I'm doing a weighted average of the models afterwards. So it's pretty important for this method to know like how much training samples were in which client. Because one big advantage we have for federated learning is that the data samples can be completely different in kind of size, for example. Like when I'm doing server-side distributed machine learning, where it's just about to distribute the load over several servers, the data sets must be similar size. But I don't have this here. And third parameter is just my metrics I have, but here for fitting, I don't have any metrics yet. And that's it for fitting. So last thing, evaluate, pretty similar. I receive the model from the server. So first thing, set the weights. Then instead of fitting, I'm doing evaluation and using my test data. And the evaluate function returns the loss and the accuracy. And then information back to the server. I will return the loss. That's interesting to the server, the length of my test set. And now I have some metrics. So let's return the accuracy. Let's have a look. And this is pretty much it. So this is already our client we can use. So let's try it out. I'll start the server up here. So server's running and waiting for clients. Then let's start partition 1, so hospital number 1. And it starts up, connected, it's ready. Let's start up second client. Third one. And now server is still waiting. So when I'm now starting the fourth client, so the fourth hospital is connecting, then it will directly start the training round. Now we only told our server that he should wait for 4 hospitals, and this will be done then. But we haven't told him how much hospitals to select for training or for evaluation. So we will use defaults here. The defaults are not pretty good for our use case, but let's stick to this. So what we will see is it will select 2 hospitals for training and all 4 for evaluation. So let's see if it works. So on the right, the 2 are training, 50 epochs, and done already. So let's look at the server. So fitting round 1 started. The strategy sampled 2 clients. Received 2 results, 0 failures. Then all 4 clients for evaluation. And we are done. We have a distributed loss of 0.46. And here you can see when you look at a training client, so he received the model, and at first on the local data had an accuracy. Can you see this? Accuracy of 63%, and then it trained locally 50 epochs. In the end, on the local data, it had around 90% accuracy, and then did evaluation with 81%. So it trained locally. Of course, now the model got collected, got averaged. To see now the effect, of course, I have to train for several rounds or just using the model. But because of the time, I will stick to this simple model. That's it already, a fully working federated learning implementation. What is nice about Flower is like, it's so simple to start. And this is really kind of production ready. Of course, I would do a little bit more for production usage, but this is a stable setup using gRPC. And now I can just optimize a lot of parameters or override something. So Flower allows me to do a lot of stuff. So when I'm looking at the server, for example, I could now in detail define how many fit clients. I need 3 clients for fitting. I need at least 1 for evaluation. I can set up the fractions to evaluate to 25% and fraction for fitting to 75% and so on. So there's a lot of details I can set. I can hand in a configuration to the clients, like defining something like the epoch. So saying like it's not about the clients to define the epochs, but I want the server to define like, please train for 50 epochs, give me back the results. I could, of course, train for several rounds, setting a config here. So I can use the Flower server config and set the number of rounds here to 3, for example. So it's pretty easy to advance the sample to a really working production product, training federatedly on the Pneumonia data. So we learned that privacy is important, of course. Transparency is important at the same time, that we have some kind of dilemma there, and that there are technologies out there tackling this dilemma. And that is possible. We introduced to you 3 technologies that are pretty important from our point of view and that are developed on actively. On the one hand, the homomorphic encryption, where you can compute on encrypted data. We have differential privacy, where we can add noise in a way that we are preserving the computation results we are interested in while destroying the original data in a way. And we have federated learning, where we move the model and the computations to the data and not collecting all the data. So it's possible for us to train models without moving the data away from where they belong and where they should stay. And hopefully we showed you how simple it is to use federated learning in production environments right now already. There are several frameworks, of course. We introduced to you Flower. There's another framework called PySift, for example, that is a little bit more coming from the research end. They're both pretty interesting, and they have great communities. So if you're interested in the topic, you should really join the communities and the Slacks. And of course, you can always contact us to join the discussion. And we are at Heureka Labs an open freelancer community. So we are all tech freelancers just coming together to talk about our projects, about technologies, giving us pull request reviews, or doing side projects like flying to the stratosphere, or doing a talk like this. So if you're interested in this, come in contact. And thank you so much for your time.